Hello, everybody. So today's talk will be given by Ashraf Aboulnaga. He's an assistant professor at David Cheriton School of Computing Science at University of Waterloo, and he's also a World Research Award winner. His research interests are on database issue in wireless and cloud computing, which is also the topic of the talk today, as well as data integration and data management on the web. Ashraf?
Thank you, Alex. So can people over the phone hear me if I stand this far from the mic? Yeah. Okay. So my talk is about application-informed tuning of virtualized environments. So let me start by mentioning that this is joint work with different collaborators. So a lot of this is joint work with Ken Salem at the University of Waterloo. Some of it is also joint work with Shivnath Babu at Duke University, along with our grad students and undergrad students. Some parts of this work are also done in collaboration with people at the IBM Toronto lab. Their names are listed at the bottom of the slide. So in my talk, I'll start by introducing why the interest in virtualization and what do I mean by application-informed tuning. And then I will talk about 3 examples of this application-informed tuning. Configuring virtual machines for database workloads, hint-based caching in storage servers, and scheduling sets of MapReduce jobs. The bulk of the talk will be about the first 2 topics because the third topic is still very much preliminary work. So, first of all, why this interest in virtualization? There is now a strong trend towards consolidation in server-side computing, where the computing infrastructure is looking a lot like a cloud, right? There's a lot of interest in cloud computing in which we use massive shared hosted clusters of servers. And why is there this interest in clouds? From the provider of computing service, it's because of economies of scale. You can get huge savings because of the economies of scale of running massive data centers instead of running small server farms. So you get cheaper servers, power, networking, cooling, etc. From the point of view of the user, it's also beneficial to use a cloud because you get efficient access to a virtually unlimited pool of computing resources without having to pay upfront costs. Okay? And for traditional IT infrastructures, even if companies are not willing or not ready to move completely to a cloud model, even within that a traditional IT infrastructure, consolidation is happening. The typical old way of running applications is to have 1 server per application. And because you need to provision your server for peak load, it means that the server is underutilized most of the time. Okay? So how to improve the situation? You improve the situation by consolidating multiple servers, by running multiple applications on the same servers. Typically, each application runs in its own virtual machines and its own virtual machine, and these virtual machines share a server. What do you get by server consolidation? So let me skip this slide. What do you get by server consolidation? You get the same general benefits you get from moving to a cloud, the same general benefits of sharing infrastructure. So better server utilization, less space, less power, less cooling. And the costs here are a bit different from a cloud environment because in a cloud environment, the dominant costs are server and power. Here, the dominant cost is administration. So you do get some savings, but basically the focus here is on easier administration. Okay? And I have some quotes here about the costs of the percentage of cost that goes into the different components of operating the server. Okay? So whether in a cloud environment or a traditional IT environment, we're moving to a consolidated infrastructure model. Okay? And when we use consolidation, virtualization becomes important. Virtualization helps us provide users with an abstract view of the computing infrastructure. You don't want users to be aware of the details of the infrastructure. You don't want users in a cloud environment to be aware of the details of which data center, which server they're using. In a traditional IT environment, you don't want users to be aware of other applications that are sharing the server with their own application. So you need to provide some abstract view, some layer of indirection between the user's view of the infrastructure and the actual implementation of this infrastructure. And this layer is the virtualization layer. And this virtualization layer, in addition to hiding the implementation detail, it also allows you to control the mapping from the abstract view to the detailed implementation. Okay? And tuning at this virtualization layer will be the focus of my talk. So the high level, the one slide summary of the objective of this research is that applications are increasingly being run in virtualized environments, typically on a cloud, but also in traditional IT settings. And in these virtualized environments, there's many configuration and tuning parameters, many configuration and tuning decisions that need to be made in the virtualization layer, and also in the application. So the question I'm trying to address with this research is, how can we make these decisions in the best possible way? How can we make these decisions in the optimal way? Okay? And my focus is going to be on application-informed tuning. Okay? What do I mean by application-informed tuning? We have lots of tuning decisions to make in the virtualization layer. Now, the optimal decisions are going to depend on the nature of the application that we're running. So the focus will be on what's the best possible way of getting application information, transferring this information to the virtualization layer, and making the tuning decisions based on this application information. Okay? And I'm going to focus on operating system level virtualization. So the model my model of the world is that users see virtual machines and virtual storage. Okay? And the specific tuning decision, the specific tuning tasks I'm going to be considering relate to tuning for virtual machines and for virtual storage. However, I'd like to point out that the same types of questions arise even if you give users a different abstract view of the infrastructure. So if you have a sandbox environment like Facebook applications or Google App Engine, you might not get this. You might not have to make the same kinds of tuning decisions, but there's still different styles of decisions to be made if you use virtualization at different levels. Okay, but for this talk, I'm going to focus on virtual machines and virtual storage. So just so that we're all on the same page, let me spend a couple of minutes talking about virtual machines. On the slide here is a typical view of an application and an operating system. So applications see the operating system sees the physical resources of the machine. When you use a virtual machine, you replace these physical resources with virtual resources. The operating system still sees a CPU, but it's a virtual CPU. Still sees a disk, but it's a virtual disk. Of course, there has to be a physical machine somewhere, and you add a virtual machine monitor to map the virtual resources to physical resources. And this virtual machine monitor has lots of tuning knobs, and our focus will be on how to tune the knobs of this virtual machine monitor. Now, you typically don't run one virtual machine on a server, you run multiple virtual machines on the same server. And this idea of virtualization is also widely applied in storage. So instead of the operating system seeing a physical disk, it sees a virtual disk. Now, of course, at some level you have the physical storage devices. They have to be there somewhere. And you have a storage server controlling the mapping from the virtual devices to the physical devices. And the second part of my talk will be about caching in such a storage server. So this was my introduction. Let me now move to talking about 3 specific examples of application-informed tuning in virtualized environments. The first example I'll talk about is configuring virtual machines for database workloads. And the problem setting here, or first, before I talk about the problem setting, why database systems? The first 2 sub-problems I'm going to talk about, configuring virtual machines for database workloads and hint-based caching in storage servers, both focus on a database system as the application. So what's important about database systems other than that I'm a database guy? Like why should people care about database systems? First of all, they're important. They are used by many data-intensive applications. And also database systems are interesting in that their inputs are constrained. They accept SQL and they serve the SQL, right? So when we reason about the workload on a database system, we're reasoning about streams of SQL queries or sets of SQL queries, okay, which constrains the kinds of inputs you have to deal with. And also, the way they serve the SQL is very highly stylized. They have these operators that get composed into query execution plans, so the way they use resources is highly stylized. And database systems have their own internal models of performance. They have a query optimizer that chooses the best execution plan, and it has a model of performance. They have memory managers that have models of performance, and so on. So basically, when we talk about application-informed tuning, the way we're going to get information from the database system, at least in the first part, will be by exposing these performance models. Okay? And database systems also pose very interesting challenges because they manage large amounts of state. I'm not going to get into these challenges in this particular talk, but this is also an area of interest when you think of running a database system in a virtualized environment. How to deal with the massive amounts of state they manage. So, the specific problem I'm going to talk about in the first part of my talk is this virtualization design problem. Okay? And here, this is motivated by a server consolidation setting. We have n database systems that we want to consolidate on one server. So we're going to run each database system in its own virtual machine, and we're going to put all of these virtual machines on one physical machine. Okay? And the virtual machine monitor allows us to partition the resources of this physical machine among the different virtual machines. The simplest thing you can do is to just give each virtual machine an equal share of resources, an equal share of CPU, an equal share of memory. The question we're asking here is, can we do better? What's the best way of partitioning the computing resources of a machine, the CPU, the memory, among different virtual machines running database workloads to get the maximum throughput? So our performance objective is maximizing the total throughput. Okay? And we're going to approach this problem as a physical design problem. Database systems have different kinds of physical design decisions that a database administrator typically needs to make. And all database systems now provide tools, advisors for automatically making these physical design decisions. Decisions like choosing which indices to create for a specific workload, which materialized views to create for a specific workload, how to partition the database among disks. Okay? And we're going to treat this as an extension of the physical design problem. So part of your physical design, if you're running in a virtualized environment, is how much resources do you get. Okay? And we're going to develop a design advisor, just like these traditional design advisors that answer questions like which indexes and which materialized views. And this design advisor will answer the question of how to partition the resources of a physical machine among different virtual machines. Okay? Now, what are the different components of this design advisor? You need oops. Yeah. We're going to assume that we know the workload of the different database systems. This is the set of SQL statements that are collected from different database systems over a fixed period of time. So we're going to run all database systems for a day and see what SQL statements they execute. And this workload description, these n sets of SQL statements are going to go into a configuration advisor. This configuration advisor has performance goals. In this talk, I'm considering the performance goal of maximizing throughput. But in the papers we have about this topic, we also have extra constraints you can add on performance. So, for example, you can constrain the amount of degradation you're willing to accept for a particular workload. Now, to achieve these performance goals, the configuration advisor is going to need to consult a performance model. Okay, a what-if model that tells us, given a certain resource allocation to a specific database system, what will the performance of the workload on this database system be like? Okay. Now, based on this performance model, the configuration advisor will come up with a static resource allocation. This is the initial allocation of resources to virtual machines. Okay. Now, if our performance model is inaccurate or if our workload changes, we will need to revisit our resource allocation decisions and refine them online. Okay. In this talk, I'm not going to talk about online refinement. I'm just mentioning it as one of the components of the solution. But I'm going to focus on the performance model and the configuration advisor. Okay? And yes, so the performance model is interesting because this is how we get the application information. This is how we get information about the specific benefit of a certain resource allocation to a database system. Okay? And what we need is a cost model that models the execution of these SQL queries we have in our workload descriptions, is throughput oriented, and is aware of virtualization, is aware of different resource allocations. Okay? And our idea is to use the cost estimates that the database system query optimizer provides. When the database system is choosing the best execution plan for a query, it enumerates different plans and it has a cost model for the execution of different plans. Now, this cost model is not aware of virtualization, so we need to make it virtualization aware. We need to create a new what-if query optimization mode in which we ask the optimizer, if you had this resource allocation, what would be the performance, what would be the throughput of this query workload? Okay? And to do that, we need to calibrate the cost optimizer to be aware of different resource allocations. So if you look at the parameters that an optimizer uses to estimate cost, you'll see that it needs to know the query, and we know the query, we know the workload for the database system. It needs some parameters about the database system, such as the database statistics. How big is the database? What's the distribution of the data in different columns? And that doesn't change according to resource allocation. But there are some parameters that model resources. Like, for example, what's the CPU cost of a comparison? What's the cost of doing an I/O? And so on. And these change according to different resource allocations. So we need to develop a calibration procedure that gets us the values of these resource modeling parameters for different resource allocations. Okay? Some database systems have this procedure automatically built in because you need to do this when you install the database system on a new machine. So when you install the database system on a new machine, some database systems will look around and see what resources they have and compute these calibration parameters based on measurements of performance on the machine. If they don't, we need to develop a calibration procedure that will be specific to a database system. It will require internal knowledge of the database system, but it will be done once and can be applied on any physical machine that we want to tune for. Okay? And basically the idea of this calibration procedure is to match as closely as possible the assumptions the database system make about the database and the query, and vary only the resource modeling parameters. Okay? So the accuracy of the cost model depends on how accurate are your assumptions about the database, how accurate are your assumptions about the query, and how accurate are your assumptions about the modeling parameters. So to find the best values to calibrate these modeling parameters, we're going to design a synthetic database and synthetic queries where the assumptions of the query optimizer are matched as closely as possible for the query and the database, so that any variance in performance is due to the calibration parameters. Okay, and the kinds of parameters we're calibrating. Here's an example from PostgreSQL. PostgreSQL has parameters for modeling CPU cost. So what's the cost of doing an operator? What's the CPU cost of an operator? What's the CPU cost of accessing a tuple? What's the CPU cost of accessing an index? There's memory parameters like how much memory you have for how much working memory you have per operator. What's the effective cache size? What I/O parameters like what's the cost of a random page I/O? What's the cost of sequential I/O, etc. So basically, we design a calibration procedure to estimate these parameters for different resource allocations. Now, once we have the values of these parameters for different resource allocations, we can consult the query optimizer, and it gives us the estimated performance under different allocations. Okay? So basically, that's it for the performance model. We expose the application's own internal cost model, in our case, the query optimizer cost model, and we need to make it aware of the effect of different resource allocations. Now, once we have that, we now have an optimization problem that the configuration advisor must solve. we have, as we vary the resource allocation to different virtual machines, the total throughput will vary. And basically, we want to minimize this total. We want to maximize total throughput or minimize total completion time. So, to solve this optimization problem, we didn't do anything fancy. We looked at the kinds of performance curves we were seeing, and we saw that they're mostly smooth and concave. And this is what you expect. So in the graphs here, what you have on the bottom axis is here you have two workloads. Okay. And what you see is the CPU allocated to one workload and the memory allocated to this workload. And then on the Z-axis, there's the total estimated cost of both these workloads together. Okay? So, for example, if you allocate 80% of CPU to the first workload, which means that only 20% goes to the second workload, and if you allocate 20% of the memory to the first workload, which means that 80% goes to the second workload, you get a total estimated cost of 500 units. Okay, and if you look at these curves, on the left you have a situation where one workload is very CPU intensive and the other is not CPU intensive. Okay, so in this case, the more CPU you allocate to the first workload, the better. Okay, in the second case, both workloads are CPU intensive, which means that if you don't allocate enough CPU to both workloads, you're going to get a degradation in performance. And if you look in the second case, the best thing to do is to allocate an equal amount of CPU to each workload. Okay? So have a CPU allocation of 50% to each workload, for example. Okay? And in both of these cases, the point of these performance surfaces is that the surface is smooth and concave. So for this work, we found that greedy search is good enough. Okay? To find either the global optimal or a local optimal that's close to the global optimal on these smooth and concave performance curves. So how does our greedy search work? We start by giving all of our workloads an equal allocation of resources. And then we try to shift this allocation. We try to shift the allocation between workloads. So we take delta units of one resource from one workload and give it to another workload. And we try every possible workload and every possible resources to find the shift that gives us the biggest improvement in performance. And to do that, we find the resource, we find the workload, where if I take delta resources away from this workload, it would suffer the least, and find the workload where if I give delta resources to this workload, it would gain the most. And I take from the one that would suffer the least and give to the one that would gain the most, and I do that until I find the local optimal. Okay? So how does this work? Here's one performance result. So in this experiment, we're using a 10 gigabyte TPCH database running on the PostgreSQL database system. And here we have two workloads. The graph shows, the blue bars on the graph show the actual execution time in minutes of both these workloads if you give the two workloads equal CPU shares. So both workloads get 50% of the CPU of the physical machine. They're both running on one physical machine, and if they get equal CPU shares, they get the blue performance. Now, if we run our virtualization design advisor, it detects that the first workload is not very CPU sensitive, the second workload is more CPU sensitive, so it decides to give 20% of the CPU capacity to the first workload, 80% to the second workload. The first workload, of course, degrades because we've taken away more than half of its CPU capacity, but it doesn't degrade by much because it's not CPU sensitive, whereas the other workload gains a lot by getting the extra CPU. So these are the kinds of performance gains we're looking for. Easy performance gains by simply making the right resource allocation decisions. Okay? So there's more details about this, and the papers that describe this are on my website if you're interested. But basically, this is the general idea. Expose the query optimizer cost model, make it virtualization aware, use it in a configuration advisor that uses a simple algorithm to achieve your performance goals. Okay? So this was the first example of application-informed tuning. The second example I want to talk about is caching in storage servers, hint-based caching in storage servers. And the problem we're tackling here is that when you go to this model of virtualized storage, you have your storage devices controlled by some storage server. The storage server has some cache capacity, and the storage clients, such as a database system, also have cache capacity. So a database system has a buffer pool in which it caches database pages. And when it requests a page from the storage server will read this page from the storage devices, and it can cache it in its own cache as well. So the question here is which pages requested by the database system should be kept in the storage server cache. Okay? So why is caching for storage servers different than caching in any other context? It's different because you have different layers of caching. You have caching in the client and caching in the storage server. And whenever you have layers of caching, the cache in the lower layer sees less temporal locality, because the very hot pages will be kept in the client cache, and the server will see less temporal locality. So there's less opportunity for benefit from caching at the storage server. The second thing is that you want to ensure exclusiveness between the client and server cache. You don't want to replicate data that's in the client cache in the server cache again. Okay? And because of these two properties, caching policies such as LRU or anything else that depends on recency don't work. And there have been specialized caching policies developed for this specific context of multi-level caching, but most of them treat the storage client as a black box. What we're looking for here is application-informed caching policies that work well with a database system. Okay? And the way we're going to do that is by using hints. Okay? The storage server, to make its caching decisions, needs to know which database pages are likely to be re-referenced in the near future. If a storage server gets a request for a page, and it's going to get a request for the same page in the near future, then that's a good candidate for caching. If a page that's requested now is not likely to be requested in the near future, then I should not cache this page. Okay? So we're going to have the database system pass hints to the storage server about the nature of its page accesses, and we're going to have the storage server interpret these hints to decide which pages to cache and which not to cache. So I'm going to talk about two approaches for these hints. One is specific to a database system. It requires knowledge of database system internals, and one is more general. So the first approach, which appeared in our FAST 2005 paper, is what we call write hints. Okay? And these hints depend on the nature of writes from a database system. Database systems write pages for two different reasons. One reason database system write pages is that this page is a candidate for replacement. When a database system wants to replace a page and this page is dirty, it has to write it back to the storage before it replaces it. Another completely different reason is that the database system might be writing the page back to storage because this page has been sitting around in memory for too long, and if there's a failure now, I'm going to have to recover all the changes that have happened to this pages for a long time in the past. Okay? So to limit recovery time after a failure, I'm going to write this page down. Okay? And what we are going to do in this approach is to tag every write from a database system as either a replacement write or a recovery write. Okay? And we're going to develop specialized cache management policies at the storage server that depend on these write hints. Notice here that it's very easy for a database system to tag a write as a replacement write or a recovery write. Okay? And in terms of the storage server, here's an example of a cache replacement policy that relies on these write hints. Here's a way to add hint awareness to LRU. Basically, if a cache is not full, then there's no need for any fancy replacement policy, just cache everything. As soon as a cache is full, you only cache replacement write requests. So you don't cache recovery writes, you don't cache reads. Replacement writes are a strong hint from a database system. Replacement writes are a strong hint from the database system that it's going to evict this page as being written. Okay? So that's the prime candidate for replacement. Because at least you're guaranteeing exclusiveness. Even if you can't guarantee a short rereference distance, at least you're guaranteeing exclusiveness. Okay? And I'm saying this is an extension to LRU, so in this case we manage the cache using an LRU list. Okay? So this is an example of a hint-based policy at the storage server. Now, we also developed other hint-aware cache management. So there's this algorithm called multi-queue that was developed specifically for storage, for caching in storage servers, and we added write hint awareness to multi-queue algorithms. We also developed our own caching policy that's based primarily on write hints. We call this the type queue algorithm. I'm not going to go into the details of these algorithms. Basically, this description of how we add hints to LRU gives you a general idea of the approach. But I'd like to show you some results. So to test this, we instrumented DB2 to record I/O traces and tag these traces with write hints. Okay? And here we're using the TPCC benchmark with a scale factor of 25. So we start with a 2.3 gigabyte database, and because of the nature of TPCC, the database grows as the benchmark runs. And we use these traces in a trace-driven simulation to compute the hit ratio in the server cache with under different policies. Okay? And what I'm showing here is one experiment where we had a 1 gigabyte buffer pool in the database system and a 500 megabyte storage server cache. Okay? And I'm showing the hit ratio under different caching policies. On the far left is LRU and LRU with hints. And as you can see, as I said in the beginning of introducing this part, LRU does not work in this context. Okay? Next up are these MQ policies, which is this multi-queue policy which was developed specifically for storage servers. I show multi-queue without hints and with hints. And as you can see, hints give you better performance for LRU and also for MQ. Okay? Now, the yellow bar is our hint-specific caching policy. And as you can see, it outperforms all other policies. The blue bar in the end is the optimal offline cache policy. So this is what you get if you know the full trace ahead of time, which is, of course, not practical in an online setting. But it shows us the size of the opportunity. It shows us what we can aim for. Okay? So this is one approach to hints. Now, the second approach, which appeared in this year's FAST conference, tries to generalize this a little. Instead of requiring specific knowledge of database system internals and how it does writes, and instead of focusing only on writes, and instead of having the cache policy be specific to a specific type of hint, we wanted to have a more general hinting mechanism. So we're going to have the application, the database system, or any other application, include all information that it thinks can be relevant for caching. Okay? So for a database system, it can definitely tell us whether this is the request type is a read, a write, and if it's a write, whether it's a replacement write or a recovery write. But it can also tell us which table is being accessed, which buffer pool is this page going to go into, all kinds of information about this I/O request that can be relevant for caching at the storage server. Okay? So it's still easy for the database system to provide all of these hints by simply attaching them to I/O requests. Now, from the storage server side, we need to figure out now which hints are useful and which hints are not useful. Okay? In the write hints approach, we did that based on our knowledge of the semantics of these write hints. Here we don't want to have a caching policy tied to specific semantics of specific hints. So we're going to have the database, the storage server, track the re-reference distance for different hint combinations, and it's going to only cache the hint combinations with a short re-reference distance. Okay? Now, the challenge here is that the number of possible hints is exponential, so we need to reduce the space required for tracking re-reference distances. And we have two approaches for doing that. One is to use a decision tree to identify which hints can, basically to reduce the dimensionality of the space. Another approach, which is the one I'm going to show here, is to only track frequently occurring hints. Okay, and when we track frequently occurring hints, we need to identify which hints. We're getting this stream of hints from the different clients, and we need to identify which of these are frequently occurring in an online way. Of course, there are many online frequent item counting algorithms. We use one specific algorithm called the space-saving algorithm that was shown to be better than others in a recent study. Okay, so we track the frequent hint combinations online, and we keep the reference distances for these frequent hint combinations, and we cache hints that are frequent and have a short reference distance. Okay, so what kind of performance do we get with this general hint approach? This is the same benchmark I showed you before, but it's a different type of graph. So on the x-axis now is the server cache size. Remember, the client cache size is 1 gigabyte. The database system cache size is 1 gigabyte. And on the y-axis is still the hit ratio. So what you can see in the bottom, the green and blue bars are LRU, which is the simplest policy you can do, and ARC, which is another policy that was developed after multi-queue that's also specific for this type of caching. But both of these are not hint aware. Okay. Now, from my previous graph, you saw that this TQ algorithm, the algorithm designed specifically with right hints, specifically based on right hints, outperforms all the others. So I show TQ on the graph, and you can see it has a better hit ratio than ARC and a better hit ratio than LRU. But then the red is this general hinting approach. The red is have the database system give you all interesting information, all information that can be potentially relevant, and have the server interpret this information to find which are interesting hints for caching. Okay, and you can see that this general hinting approach outperforms all the others, because it definitely detects that the replacement writes are good candidates for caching and the recovery writes are not, which is what we had in the previous algorithm, but it also detects other caching opportunities based on different types of hints. Okay? And the top line is still the offline optimal, which just shows you the size of the opportunity we have. Okay? So this is the... Yeah, I'm going to skip this slide. This is the second problem. This is the second type of application-informed tuning. In the last few minutes, I'd like to talk about a third problem, which we're just starting to look at, which is scheduling for sets of map-reduced jobs. Okay? So here we're shifting from the application being a database system to the application being map-reduced jobs. And the problem we're tackling here is how to run a set of map-reduced jobs on a cluster of machines to minimize the total completion time of these jobs. Okay? And with MapReduce, you have lots of tuning decisions to make, like how many machines to assign to a specific job, which machines will run which jobs, and how do I schedule the jobs on the machine. So I have a batch of MapReduce jobs, a cluster of machines. My goal is to minimize the task span, the total completion time of all these jobs. Okay. Now, for this can be done in any MapReduce scheduler. In our case, we use Hadoop, the well-known open source implementation of MapReduce, and we run the Hadoop nodes in virtual machines. So every job has a cluster of virtual machines that are each running Hadoop. Okay? Why do we do it this way? Because this helps us get isolation between the jobs, and it helps us in flexibly allocating resources to these jobs. However, it's this problem of scheduling MapReduce jobs can be tackled within traditional MapReduce scheduler without using virtual machines. But for the next few slides, I'm going to be talking about running Hadoop nodes in virtual machines, and the question I'll be addressing is how to allocate virtual machines to Hadoop jobs, or how many virtual machines for each Hadoop job, and also how to schedule these virtual machines on the cluster of physical machines. Okay? Now, what do we need to solve this problem? We need two things. We need a model of performance of these Hadoop jobs, and we need a scheduling algorithm that's based on these models of performance. Okay, these Hadoop jobs are interesting, or introduce a new component or a new aspect of tuning in these virtualized infrastructure, which is experimental model building. For database systems, we relied on our knowledge of the internals of the database system, and we relied on the internal performance models the database system itself provides. For a Hadoop job, we don't have an internal model of performance. Okay, so in this setting, a very good way, or in my opinion, the best way to model performance is to use experimental model building. Okay, run experiments to sample the space of possible job executions, the performance as a function of different parameters, such as different database size, different data sizes, different number of nodes, different data distributions, if you will, and then fit a statistical model to observe performance. And one question that arises is, where do I run these experiments? Since I'm using a cloud infrastructure, I have a capacity to run experiments, but there are still challenges that I need to address. First challenge is, how do I design these experiments? Okay, do I have a full factorial design, or do I have something more fancy to minimize the number of experiments I need to run and get the most improvement in accuracy per sample? Okay. The second challenge in this area is, how do I scale a model from a sample to that's based on a small sample? How do I run a model on a small cluster, on a small data set, and scale the performance? How do I run experiments on a small cluster, a small data set, and scale the performance to large cluster, large data set? Okay, and I don't have an answer yet to these questions, but let me show you what we do now. What we do now is, we have a fixed data set, so we know the data set we're going to be running on, and we simply want to model the performance as a function of the number of nodes we give to a specific job. Okay, so we run experiments on different numbers of nodes, and we fit a power regression to the observed execution time. We also classify jobs as CPU intensive or IO intensive, because that's going to help us when we allocate jobs to physical machines. Okay, so here's an example of what we get. So these are two Hadoop tasks. The first, the blue one is sorting. We're sorting, I think, a small amount of data. This is a sample task that comes with Hadoop. The red task is k-means, one run of k-means clustering over synthetically generated data. And what you see on the x-axis is the number of nodes you assign to every job. The y-axis is the execution time in seconds. And solid is the actual time. Dotted is the estimated time according to our model. You can see that our model is quite accurately tracking the actual execution time of the jobs. And one thing you can see here is the reason why you have this scheduling opportunity. For any one of these jobs, the more nodes you give the job, of course, the faster the job will complete. But then there's this knee in the curve. There's a point of diminishing returns. There's a point at which adding more nodes give you diminishing returns. So if you have a set of jobs, you have an optimization problem to decide how many nodes to give to each job. Okay? And this is what our scheduling algorithm will do. It will decide how many nodes to give to each job, and also how to allocate the jobs to the physical machines. Okay? Because we know the resource. Remember, I told you that when we're modeling these jobs, we classify them as CPU intensive or IO intensive. So we can try to pack as many of these jobs on the machines as we possibly can based on our understanding of the resource consumption. Okay? So we have two algorithms, which I'm not going to get into the details of. One of them schedules pairs of jobs. So I have k-means and sort. Basically, given a set of jobs, I look at these jobs a pair at a time, two at a time. Okay? And I try to schedule them. I try to schedule the best two jobs that go together on the cluster at any one point in time. And I do that until I have scheduled all my jobs. Okay? Now, we also have another scheduling algorithm that is based on an integer programming formulation of this problem. This can schedule any number of tasks concurrently on the cluster, but we're still struggling with integer programming solvers to come up with an efficient and with a good and efficient solution for our integer program. Okay, but the point is that once you have the performance model, once you have the performance objective, you can formulate an optimization problem and solve this optimization problem in a standard way to get the best schedule. Okay, and in all cases, the scheduler, when the schedulers try to allocate the virtual machines to physical machines, they try to overcommit the physical machines to jobs. Okay, so if they see that I have, for example, a machine that has IO-intensive jobs but no CPU-intensive jobs yet, they try to add CPU-intensive jobs. So basically, we're running these Hadoop jobs in virtual machines. We can take a physical machine with 4 CPUs and 2 disks, and on this machine run virtual machines with a total of, say, 8 CPUs and 2 disks. 8 CPUs and 3 disks. Okay? Why can we do that, or what's the advantage of doing that? It's because we know whether these jobs are CPU intensive or IO intensive. Okay? So what kind of performance results do we get with this? As I said, this is still work in progress. So we're starting with a tiny cluster of 9 machines and 4 really small Hadoop tasks. One is sorting, another is k-means clustering, building an inverted index for Wikipedia, and pairwise similarity of Wikipedia documents based on this inverted index. The sort task is something that's available as an example task with Hadoop. The other ones are things we developed ourselves. And we form different workloads by combining different instances of these tasks. Remember, the idea is that I have a set of MapReduce jobs and I want to schedule them. So what's my set of MapReduce jobs? In one case, I have 2 sort jobs, 2 k-means, 1 invert index. In another case, I have 2 sorts, 1 k-means, 1 invert index, and 1 doc similarity, etc. We can form different workloads by choosing at random from this set of tasks. And here's the performance we get. What I'm showing is, for the 3 different workloads, the completion time in seconds. Blue is what you get when you run these tasks one after the other, giving every task the full cluster. Okay? Green is what you get with our pairwise task scheduler. So it tries to pack things on the cluster, but it can only pack 2 jobs at a time. Since we have a small cluster, 2 jobs is pretty much what we can. Mostly we can do very well by supporting just 2 jobs. Okay. Red is our multitask scheduler, which can combine more than 2 tasks on our cluster. Okay, and you can see that you get some extra performance improvement. The performance improvement is not dramatic, but then again, you didn't have to do much work to get this performance improvement. It's simply by doing the right scheduling and resource allocation decision. Okay, so that's it for the third part of my talk. So basically, to conclude, the computing infrastructure we're using is becoming increasingly virtualized, which means that applications are increasingly being run in virtualized environments. We need to make tuning decisions at the virtualization layer and also at the application layer. And what I'm arguing in this talk is that these tuning decisions should be application informed. If you make these tuning decisions in an application informed way, you get easy and cheap performance gains. Okay? Now, at the abstract level, this is motherhood and apple pie. Who would argue against application informed tuning? What I showed you in this talk is 3 concrete examples of how to make these application-informed tuning decisions. For configuring virtual machines for database workloads, for caching and storage servers, and for scheduling MapReduce jobs. So that's it. Thank you, and I'm happy to take questions.
Any questions?
Yeah, so question I have is, you use the information from the applications in order to tweak the virtualization and make it faster. How much information does a human need to provide, and how much information can be automatically detected?
So the goal is to have most of the information automatically detected. Yeah. So for example, for the first part of the talk, all the database administrator, the human, needs to provide us with the workloads. So here are the database systems I want to combine on a storage server, and here are the workloads that I've collected for each database system. Actually, the human doesn't even need to provide the workload. The human simply needs to start and stop workload collection on the different database systems. For the second part of the talk, the human doesn't need to provide anything. For the third part of the talk about scheduling MapReduce jobs, the human will need to provide the tasks to be scheduled, and as we refine the modeling approach, maybe the human will need to be involved in this experimental model building as well. But at a high level, the goal is always to minimize as much as possible human involvement, which is why you get as much information as you can from the application itself.
Well, I have another question about MapReduces. This is really useful if you have a MapReduce that you need to run every day, because you can clearly tweak your MapReduce before launching the system.
Yes.
But what if you have a super duper big MapReduce that will run for hours and hours, and you don't want to take the time to tweak it? Can you tweak it during the process where parameters will be changed online?
In principle, yes, that's possible. Again, we'd have to go back and see how we're going to obtain the performance model of this MapReduce job online while it's running.
Yeah.
I mean, what I'm assuming here is, in what I've shown you, the MapReduce tasks were modeled offline. So basically, we run the experiments on MapReduce tasks, and we run the same MapReduce tasks. Now, if you take this a step further, you'd run MapReduce, you'd build your model based on some tasks, and you'd run tasks that don't necessarily have to be the same, but they have the same characteristics. They're accessing the same data sets, for example, doing the same kinds of computation and so on. Now, if there's a task that you haven't seen before at all, then in principle, it would be great to be able to do this scheduling online, but then we'd have to figure out how are we going to model the performance of this task in an online way, which is something we haven't figured out yet.
Okay.
Can we model based on, like, say, if it's a multi-hour MapReduce job, as Claude Guy said, could we just do based on after the first hour of execution, we get some data, and maybe we know how far we are in the process, and then we can estimate and recalculate and or give more resources to the virtual machine where the MapReduce runs, or pack differently the job on other machines?
Definitely, yes. I mean, I have some work with Shivnath Babu and Mumtaz Ahmed, my student, on this experimental modeling for long-running queries. And in this work, it makes you get more bang for the buck if you do this kind of optimization decisions for long-running queries, because there any refinements in the infrastructure will have a long time to have their impact. Okay, whereas if it's short-running queries, even if you make the best decision, there's not that opportunity for performance improvement anyway. Now with MapReduce job, that takes it a step further, because when I talk about a long-running query in a database setting, it's typically minutes, 10 minutes, 20 minutes. When I talk about a MapReduce job, it can be hours, right? So definitely, yes, you can collect information during the first hour of running and use information for tuning later on. Actually, you can explore the space in the first hour of running. I mean, you can run experiments, if you will, while the job is still running. You can explore parts of the space that might not be optimal, but you have hours and hours to run anyway. So it's okay to make a bad step just for exploration purpose. So in principle, yes, definitely this can be done, but basically we haven't worked out the details yet. I don't have a solution to present you that does this.
Anybody else? Jed, you have a question?
So I'm just wondering, besides making these optimization tuning decisions based on the applications that you're dealing with, are there any other techniques? So besides application-informed decisions, are there different things that you may be able to look at? This is, I guess, out of the specific fields that you're looking at, but I'm just wondering if there's any other techniques that are out there. So basically, right now, you're making these tuning decisions based on the applications
Yes.
that you're dealing with. Are
Yes.
there anything else that you could do besides that? It's just a general question.
If you don't have application information, you could still get some benefit by doing these tuning actions. And if you don't want to collect information, you can still do things like look at resource consumption locally and do local decisions based on that. You know, the goal is to do better by incorporating application information.
Yes, it's about your integer programs that you use for computing the best scheduling. How big is this optimization problems, and how long does it take to solve?
It's fairly large. So we had a variable for every node of the cluster and every job. So the number of variables is the number of jobs times the number of nodes in the cluster.
Okay.
How long did it take to solve? Depends on the solver, of course.
Yeah.
Typically, minutes.
Are those variables 0, 1
Binary,
variable?
yeah.
Binary?
Zero, yeah. Yes.
Okay. Okay, and you say you solve it in minutes?
Yeah.
Okay, good.
How does that compare with how would that compare with the savings that you're getting out of the better schedule?
You still get savings. Like if you factor in the cost of solving the integer program, you still get significant savings.
So in the first part of the talk, you also mentioned you showed the two workloads and you showed how they would model the CPU and the memory utilization, and that greedy would work would be good enough to obtain the best resource allocation. Would greedy still be good enough if you have a larger space of jobs, like 10 jobs or more jobs? Would the
Yes. I mean, what I've shown is 2 jobs because that's what I could fit on a 3-dimensional graph. But we've looked at this for larger numbers of jobs, and we still find that
so there's just
greedy.
one
So basically, in the larger number of jobs, we don't do visualization. Of course, what we do is run an exhaustive search and run the greedy search and see how close the optimal we get from exhaustive search is to the optimal we get from greedy search.
I see.
And we typically find that they're very close to each other.
All right.
I mean, there's basically here greedy search is. We're using greedy search because it worked good enough for us, but there's no reason why we couldn't use more advanced a combinatorial search if we need to.
Okay, thank you. I think that's it. Thank you.
Thank you very much. Are there any questions from the people on the phone?
All right, thank you.
Thank you.